Good evening, everyone. As I had promised to you, the next class will be of Coulomb's law. But it will not be worthy if we leave the conical pendulum. So, today we are going to discuss the conical pendulum. First of all, we try to know what is the conical pendulum. Let us see. So look at here. Here is a string, say massless string. Say it is a bob of mass m, supposed to be very small mass, is attached to its lower end. So this setup, a bob of mass small m and massless string, may be used as a simple pendulum. Look at how it behaves as simple pendulum. So let us we assign it, say some angle here, and from this position let it go. Look at here. So if it oscillates in this way, then this is known as a simple pendulum. By the same setup, it may behave as, or it may we take up as the conical pendulum. Look at here how. If we rotate like this here, so this same setup, a bob of mass small m and a string, now taken as the conical pendulum. Look at here. If it rotates in this way, then this is known as the conical pendulum. So look at here. It depends how we rotate it, that is on the angular speed, and hence this string together with the bob makes an angle theta from the vertical, or it also depends what is the radius of the horizontal circle in which this bob of mass rotates. Both of them, the horizontal radius and the angle, this string together with the bob makes with the vertical. Say look at here, this finger taken as vertical, say the bob position at some angular speed, say here, then this string makes an angle, say look at here, alpha theta, you may call it, with the vertical. My index finger here taken as the vertical, and here is the horizontal radius about which it rotates like that. Okay, so radius. And one more thing is also here. So if say at this angle, say we may find the vertical height. This is point mass like. If it is some finite mass, then we think of center of mass or like that, but it is a very small mass, bob of mass supposed to be very small. So taken as a point, if it taken as a point, then this is also the center of mass. Okay, so this height from here to there, this height also depends on the angular speed. So we will take up dependence of these quantities on the angular speed later on. Firstly, we want to know its time period. Now, again, we have another setup, may be taken as the conical pendulum. Suppose this is a light rod and some small mass is glued here and it rotates like so, it also taken as the conical pendulum. Second way. And third way, suppose it is a massive rod, mass m, length L, mass is distributed uniformly, then this setup or this combination may taken as the conical pendulum. The way it rotates, look at here, massive rod. This is also known as the conical pendulum. Finally, we will take a problem on that. Now, what we are going to study in case of the conical pendulum. For the clarity, we list it firstly and then we will take up one by one. The conical pendulum. The conical pendulum. In this, we are going to study the time period. The time period. Secondly, here we will take up torque. How torque is associated with the conical pendulum. It will be very interesting because today we are going to see all the time torque is equal to I alpha may not hold good. That is why it is very interesting. Today we will see how. And then we will take up, say here, angular momentum. Angular momentum. So these three things we are going to take up in this article, the conical pendulum. To understand these things comfortably, conveniently, so we will take up the conical pendulum of the form like here, a string and a bob of mass attached to its lower end, and it rotates the way I provide the angular speed here. Look at. So we are going to study on these things on the conical pendulum of the type string with the bob. However, it may behave as a simple pendulum the way it oscillates. And look at. So let us see here. One by one. So firstly, we are going to take up here the time period. The time period. The time period. Look at here. Firstly, we are going to make a horizontal circle on which the bob rotates. Look at here. So here is the peg or the point of suspension about which this bob together with the string rotates. So here center of the horizontal circle, see here bob of the mass small m. This is the radius of the horizontal circle, small r. This is length of the string, supposed to be massless, small m. Now, as usual, just we are going to investigate what are the forces acting on this bob. We are performing this experiment near the surface of the earth, and we have discussed in the earlier classes the acceleration due to gravity is not constant either magnitude wise or direction wise, but for practical purposes we take it is constant, and at the same time also pointing vertically down. However, this assumption is strange, bizarre, because as we all know that the force on an object near the surface of the earth or at the surface of the earth is towards the center. That is why it is very special approximation I am seeing here in this class. That's okay, fine. Give you to think more and more about that. And the next one is the force of tension, because string is massless, inflexible as well, so it provides tension. And apart from these two forces, is there any forces? Of course, there is a resistance, air friction, viscous force, might have been buoyant force. But for the practical purposes, or to understand this article, the conical pendulum, we have to assume all such kinds of forces are absent. That is, no dissipative forces acting in our system. All the time we are investigating these things, because this creates the curiosity in you. That is why. Now one more things, other objects here, books, fan, wall, mercury tube, might have been sun, moon, asteroids, any celestial bodies. Are they not exerting any force? Answer is yes, they are exerting. But we are interested in few of them, that is, these are also approximations, because their effects are negligibly small. Still we have to neglect all those kinds of forces other than the force of gravity here and the force of tension, to keep in mind like that. Now the force mg is vertically down here, mg has the force of tension T. One misconception here among the physics fraternity is that, say this bob is moving in the horizontal circle with constant angular velocity So the force towards the center. Yeah. But keep in mind, these forces toward the center via acceleration toward the center came by these forces, these two forces in fact. So if we are interested in the motion of a particle or an object, then we are interested only on those forces which are acting on our system. After the exerting by the external agency on our system, then this acceleration generated. So mass times acceleration force we are going to not consider here, because these forces, or you may call this acceleration, is generated by these two forces only. So we ignore such types of concept when we are dealing the motion of an object. Keep in mind. So resolve this tension T. So this angle is alpha. So this is here T cos alpha, and here toward the center is T sin alpha. Here also very interesting thing is here. Look at again. Now look at here is vertically below, and now I am giving the angular speed just increases, just increases, just increases, just increases. Now just I keep the angular velocity constant. So what will happen up to this angle? Look at here, angle gradually increases as we as I provide this angular velocity, or you may call it speed. The angle made by this string, the vertical, gradually increases. Gradually increases as the angular speed increases. So till we keep the angular velocity constant, there is an angular acceleration. And look at here, at the same time radius is increases and height is also increases. Suppose this is the reference level. So if rotates like from here in this horizontal circle, the height is also increases of this bob from the reference level. So the bob also going up. So who is pulling up? Look at here. This is T cos alpha. mg is vertically down. The bob is going up, as we have seen right now, up to the angle alpha, say T sin theta or T sin phi at some instant, must be greater than mg. That is why the bob is going up, otherwise not. And at the same time it is moving on the circle, so there must be force towards the center. Now this time, look at here again, this time, now I have keep the angular velocity constant, keep the angular velocity constants. Once angular velocity is constant, then there is no angular acceleration. So and therefore T cos alpha must be equal to mg, and T sin alpha must be equal to m omega square into small r, radius of the horizontal circle. Look at here r. Now we are in comfortable zone. Write down for the vertical equilibrium. For vertical equilibrium, T cos alpha is equal to mg. Take it equation number 1, and the second one, T sin alpha is equal to m omega square small r. This is taken as equation number 2. Now I have taught you in the previous classes is that angular speed and angular acceleration. These two parameter is related to the rotational motion. Whether a point mass is rotated or the body is rotated about certain axis. Okay, we will see these things in very detail in rotational dynamics. Okay, but one more thing is here, angular speed and angular frequency. That's our motto here. So I have taught you in general these two physical quantities are different. But look at here again. But here when angular velocity is constant, say at angle alpha from the vertical, so here angular velocity and angular frequency became same. So sometimes angular velocity and angular acceleration are same, but in general these two are not same. So here angular speed we may take it as angular acceleration. Okay, sorry, angular acceleration, not angular frequency. So angular speed is as good as angular frequency, but in general these two physical quantities are not same. Angular speed is rate of change of angle in the process of rotation, but angular frequency is, we consider in case of AC, any AC phenomena, any SHM phenomena, any periodic phenomena, any oscillatory phenomena. Okay, so T sin alpha is equal to m omega square r. Now we divide equation number 2 by equation number 1, comma, we get what we get. Look at here. So we get here tan alpha is equal to omega square r over g. What is tan alpha? Look at here. This angle is 90 degree, however it is not looking 90 degree, but it is 90 degree. So what is this length? Look at here. This length is from here, this is the L, and this is L cos alpha, and this is smaller. So tan alpha is perpendicular by base. So here perpendicular is a small r and the base is L cos alpha. So write down here r over L cos alpha. This is equal to omega square r over g. So here a small r is defined as well as not equal to 0 because there is some radius of the horizontal circle. So cut it here. It will give you omega, the angular speed, as good as angular frequency. Here in this particular case, this omega is equal to g over L cos alpha square root, however plus minus, but angular frequency or angular speed here are positive, so we have to take positive square root. Okay, so this is the omega. Now time period is, as we know, time period is equal to twice pi over omega. Now it comes out to be twice pi square root of L cos alpha over g. So now we compare this to the simple pendulum. We compare it with the simple pendulum. Look at here. So this cos alpha factor in the square root is extra. Why we call like this? Because we have been derived the time period of the simple pendulum as 2 pi under root L over G. However, this is the case when length of the string is very smaller than the radius of the earth. Okay, and the experiment is performed near the surface of the earth. So that is why. So just we are recalling these things to mingle what we have read up to the types of the pendulum. So that is why. So here the time period. So first article, the time period has been cleared here. But one more interesting thing in this case is from here. So what is cos alpha? The cos alpha from here, look at cos alpha is equal to what? From here we write it down. This implies from here omega square L cos alpha is equal to G. The acceleration due to gravity magnitude. This implies cos alpha is equal to G over omega square L. As I have taught you in the beginning of the class, alpha, the angle made by the string together with the bob with the vertical, omega, the angular speed, as I provide or as we provide length L and G supposed to be constant, we have assumed already. Okay, so we have to see the dependence of alpha and hence cos alpha on omega. In fact, omega, how omega decides alpha. So firstly, if omega is equal to under root G over L, then what will happen? In this case, we look, cos alpha comes out to be 1. Then this implies alpha is equal to 2n pi, n belongs to integer. But in this particular case, particular physical situation here, n is equal to 0, give you alpha is equal to 0. If we take n is equal to 1, then 2 pi in this particular physical situation is not give you anything. As we put n is equal to -1, -2 pi, so such solution exists in mathematics. But here in this particular physical situation, we have to exclude these values of alpha. Only we have to take acceptable values of alpha is 0. So look at here, if alpha is equal to 0, alpha is equal to 0, omega is, look at here, there is some omega is. If alpha is equal to 0, so what about sin alpha? Cos alpha 1, then sin alpha 0, and sin alpha 0, cos alpha 1. So as we know, 90-degree situation like that. Okay, I am not going to indulge on that. Alpha is equal to 0, and still it has got angular speed. Look at here, rotated. The bob is all the time vertically below, still rotated. Look at here, the very interesting situation. Very interesting situations. Such types of the conical pendulum. Yes, there is angular speed. At the same place it is rotating. Now, take the second case. Case second here. Omega is less than under root G over L. Then what will happen? What will happen? If this is less than 1, then right side becomes greater than 1. As we know from trigonometry, the maximum value of cos alpha is 1. And right side comes out to be is greater than 1. Left side maximum value 1. So no way we are going to accept such angular speed for this conical pendulum. So this implies cos alpha is greater than 1, mathematically not acceptable. If mathematically not acceptable, definitely we cannot apply in case of physical situation. However, sometimes mathematically it is good, but still physically not applicable. That's altogether different issue. But if mathematically not acceptable, no way to apply in any physical situation. Okay. So these are things now. Now the third case arises here. Here's the case 1. Case 2, and here's the case 3. The angular speed is greater than under root G over L. G over L. Greater than, then how much? Look at here. Again look at here. Just by providing more and more angular speed, what will happen? Then almost become horizontal. Almost horizontal. But in practical situations, I have shown you, but look at here, cos alpha is what? G over omega square L. Theoretically, if omega tends to plus infinity, might have been minus because no way to say here because square is there, the square of real number is also positive. So that is why if omega tends to plus infinity, then this quantity comes out to be nearer to 0, then cos alpha 0, and one of the acceptable physical situation here, one of the acceptable physical solution is here alpha is equal to pi by 2, means it becomes horizontal, in principle when omega tends to plus infinity. Look at here, when omega tends to plus infinity, then only then. That is why we have to call and we have to provide maximum. How much? Look at infinity. Very large value, infinite value. That's the theory. Practically very large. Okay. Now, one of the cases just I'm going to look at here, T cos alpha. Look at just case 4. We take here case 4. Then omega is equal to under root G over L. Then cos alpha become 1. What is the consequence of this? Look at very carefully. T cos alpha is equal to mg. This implies T is equal to mg because cos alpha is equal to 1. What does it mean? It means that it is vertically below. Bob is all the time vertically below. no matters what is the speed you are providing, angular speed, you are providing it all the time vertically below. Look at here, all the time vertically below. However, this angular speed provided from this point, not from here. Just I am showing you, it is hard to provide from this position. Manually it is very hard. Mechanically it may be possible. Look at here. How large you are providing the angular speed, no matters at all. Matter is, it is all the time vertically below. That's okay. But one of the most important consequences is that it is rotating very fast, very fast. And if someone perturbed it, taken somehow aside, then look at here, speed is very large. We have seen earlier, if speed is very large, then it becomes like that, horizontal circle like that. So if we perturbed it slightly, then we got, and then we have provided some angle here. So it fly away very fast, very fast. Very interesting things to hear. So that's give you the very interesting feeling about that. If you are going to perform like that, so definitely in conjugation with the two friends, you are going to perform an experiment. If someone is providing a speed and another one is just deflection is there, so it move like very fast, very fast, very fast, fly away like that. So these are the consequences of the conical pendulum in terms of its time period. Now the next one, we are going to discuss the torque. The next one, number 2, taken as torque. This is the horizontal circle. We are going to find torque and angular momentum only when the bob of this conical pendulum moving with constant angular velocity. Okay, keep in mind. So here is, say, the point of suspension. Here is the center of the horizontal circle, and here is, say, the bob of mass m. So rotating in the horizontal circle with the same angular velocity. Okay, the point of suspension here. Forces again, as we know, the force of gravity mg and the force of tension T. The only two forces acting on this bob, and we have to find the torque. So we have 2 points, say the center of the circle, say center of circle, say O, the point of suspension here, say A, and now this point, say B. So we have to find the torque about the horizontal circle. Mind you, this radius of the horizontal circle changeable as we provide the angular speed, but we have taken angular velocity and hence angular speed constant. That is why we are talking like that. So here, say the radius r. Okay. Now we want to find the torque about the point O. Torque, say O. So basic definition of the torque, as we all know, R cross F. R cross F. R cross F. Now we want to resolve, say this is the angle alpha, then certain angular velocity taken as constant. So resolve this one here. This is t cos alpha. Here is the t sin alpha. Look at here. In the course of motion, t cos alpha balances mg. So these two forces altogether gives you zero resultant. So if the force is zero, so torque will be automatically comes out to be zero. Okay. Now second one, t sin alpha pointing towards O. Look at there. Look at there. So if the force pointing toward the point about which we are interested to find the torque, then moment arm or the lever arm comes out to be zero. And hence, what we find? Net torque comes out to be zero. Now, we found net torque comes out to be zero. So, the net torque about this center of the horizontal circle comes out to be 0 unit. That's the way. We have taken the approach like that. You may take another approach too, because here the point, take these two forces and then vector law, and then you will find the same things. But this is the quicker one. In short, you may call it trick. Trick is nothing. If you do the things in some what is called short way, then you call it trick. It will develop gradually if you are studying more and more. Now what about the point A? Now we want try to find the torque about the point, say A. Look at here. Now we are thinking in terms of tension and mg, not in terms of thinking t cos alpha and t sin alpha. Why this time so? Because this force of tension is just this line of action of this force of tension is passing through the point about which we are interested to find the torque. That is why this time we do not resolve this one. The torque due to force of tension which is acting on the bob crosses through the point. So the moment arm and the lever arm comes out to be 0 and hence the torque is 0. We think about here mg. So here is the radius vector like that, r vector. Here is the mg vector. So this is the point. This is the line of action of the force is like here. This is the line of action of mg. So what is the moment arm? Line of action. Look at here. This is the line of action and this give you moment arm. So what is this moment arm? This is L sin alpha. Okay. For direction, you may take like r cross mg, or you may take moment arm may be taken as a vector. In short, if you are finding the torque not by basic formula r cross f, you are taking the moment arm or the lever arm. For the direction, because torque is a vector physical quantity, however it is axial vector, not a true vector or proper vector, because we will see in the vector class on parity transformation. The torque vector will not change its sign. That is why it is called axial vector, or you may call it pseudo vector. But majority of vectors change its sign on the parity transformation. What is the parity transformation? We will see in the vector class. Okay. So the torque is an axial vector. Okay, angular momentum as well, axial vector. So here, so it is worthy to take momentum as a vector to see the direction. So here like that, here is the action of the force mg down. Take it as a vector. Momentum may be taken as a vector. So direction like that. Clockwise means inta the board. So here mg the force and the moment r is L sin alpha. However, going inta say you take a small cross in the small circle. So this is the torque about point A. So we have been found the torque about O and torque about A. The obvious question, are we in a position to find torque about any other point? Of course, we are able to find. We may take any point in space anywhere else. But in most of the problems, what the people are asking, only 2 points, center of the horizontal circle and the point of suspension. Okay, you may take any other point too. If one can ask, then okay, then it is the measure of measuring the momentum and lever arm that creates problem, but it may be solvable. That's okay. Now we are going to find the angular momentum in a similar fashion. The third one and last one is the angular momentum. Angular momentum. Now we are going to see here what is the actual definition of torque and the angular acceleration. How torque is related to the angular acceleration. The relation, as we know, it is applicable always. Then what is the relation? As we know here, relation is torque is equal to I, moment of inertia about the axis with the alpha, and torque will going to be measure alpha. Look at here. Is this relation be good always? Answer is no. It is not good always. So just we are going to see how this relation not always hold good. So angular momentum as the same about this point, center of the horizontal circle. Again we will take out the point of suspension. So firstly we are going to find about the center of the horizontal circle. So angular momentum usually we represent with a capital letter L. L-O. What is the basic definition of the angular momentum? R cross P. R cross P. What is P? That is the matter of interest here. If it is rotating with say certain constant angular velocity, look at here. So this bob is moving in a horizontal circle. It means velocity is tangential to the any point on the circumference. And the radius, look at here, it's moving like in this radius. So this is the radius and this is the tangent. Look at here, the radius and tangents are perpendicular to each other. Okay. So for the sake of convenient, we write this one as sin 90 degree. Because this is a vector quantity, we have to write direction 2. For direction, look at here. For direction, so this is the horizontal in the direction in which radius vector, tangent to this radius is the velocity, means the linear momentum vector. So like that here, say this is 90 degree. Okay, so r cross p, it means it is going in the board, coming perpendicular and coming towards us. But here in this practical situation, realistic situation, what is the direction of this angular momentum? Look at here. Look at here. In this direction, radius vector. In this direction, horizontally, both are horizontal. Here is the radius vector and here is horizontal. So this is the anti-clockwise sense. So comes out to be vertically up. Comes out to be vertically up. Look at, if this bob goes here in this position, so here is the radius vector and here is the velocity or the linear momentum vector. So again comes up. Again it comes here. So here is the radius vector, here is the velocity vector, and hence the linear momentum vector. Cross products goes up. So we see that at every one of the point of this horizontal circle, direction of the angular momentum comes out to be vertically upward. Vertically upward. So direction is vertically upward. Vertically upward here. Direction for direction, vertically upward. Vertically upward. It is not able to see. We are not able to see, in fact, in this board, because mostly in 3D space, and we are depicting the situation in the two-dimensional board. That is why. Okay, keep in mind all the time what we are doing, what we are seeing. We did the experiment in 3D space. We are depicting the situation in the 2D space. That is why. So what is this R? Okay, this P is MV sin 90 degree. Sin 90 degrees comes out to be 1. And direction is as M V velocity. Look at here, velocity. This is omega cross R. Again, omega and R both are perpendicular to each other. That is why it is horizontal. Omega is vertically up. This is the radius, horizontal. Omega cross, so that is why tangential. So angle between them is 90 degree. That is why I am telling you. However, in the physical situation, angle between angular velocity vector and radius vector in majority of cases comes out to be 90 degree. But in mathematics or maybe in some physical situation in gyroscope like that, so angle may be differ from 90 degree. That is why I am showing like that, because the angle is 90 degree. Again see here. Again see here. So velocity omega about this axis vertically up. Radius of this horizontal circle is like that. So this is 90 degree. This is the omega and this is the radius vector. Okay. So this is omega cross R. So this is the R and this is the 90 degree. So this is omega R, M omega square R. This is the, and it is constant. The angular momentum about the point O or the center of the horizontal circle comes out to be constant. Okay. Now let us see what about the point A. LA. Again we see here R cross P. magnitude of radius vector for this point about A is itself the length of the string L. Velocity is tangential. Look at here again. Say this is the string, this is radius vector and this perpendicular to that. Look at here, perpendicular. Velocity is tangential, horizontal circle, tangential. Here is the string, say it is moving in horizontal circle. Pick up here. So this is the radius vector, this is string taken as radius vector from this point to that here towards the bob, and the tangential here 90 degree angle. Look at here, 90 degree. 90 degree. This is the velocity. Okay. So R is here is L, P is mv, sin 90 degree comes out to be 1. What about direction? Because as we know, say taken as vector A cross vector B, how one can find the direction? What is the definition of vector A cross vector B? Vector A cross vector B is equal to modulus of vector A multiplied modulus of vector B multiplied sine of the angle between them multiply unit vector n. This unit vector n is perpendicular to vector A as well as on vector B over the plane containing vector A and B, because given two vector B always coplanar, that is they lie in the same plane. What we pick up from here? From this definition, R cross P is perpendicular to both vector R and as well as on vector P. Okay. So then what is the direction of this? Look at here. So this is perpendicular to both. Here the some unit vector say n. This unit vector n. Unit vector. Mind you, unit vector. There is no unit of unit vector, but magnitude is 1. Unity. This unit vector perpendicular to both R and P. Now look at here. This is my spectacle. Look at here. So this is the string and this is. So look at this, the string, and this is the velocity v perpendicular to both. This is the R vector, this is the velocity vector. So the angular momentum vector is perpendicular to, why not on this R vector? This is supposed to be length of the conical pendulum. So this is the L vector. So whole thing is rotated like that. It means look at here. Look at here. So the angular momentum vector about this point of suspension, if the bob is here, then there. It goes bob like that, then here, there. If like that, then this like that, here. If like that, perpendicular. And at the same time, because it's moving with a constant velocity, so it is always perpendicular to both radius vector, that is the length of the conical pendulum, and the velocity vector, supposed to be constant. So it traces a cone like that. So this is the angular momentum vector. If the bob is here, bob is here, bob is there, then like that, like that. So it is like that. It is like that. Look at it, traces a cone. Traces a cone. Traces a cone. Okay. So we will see of that. What is the consequences of that? Because we have to see all the time torque is equal to I alpha is not applicable. How and why? Just I am going to discuss of that. So before indulging in that, just we have to take some input here. How we find the change of a vector which is under rotation with infinitesimally small angle. In other words, if vector rotates by very small angle, then what will the change of that? Just I can discuss here. Firstly, suppose here is the origin and say here is the vector r. Now this vector r is rotated. It means in a circle like that. Look at here. However, angle of rotation we are going to take very small, infinitesimally small. But for the sake of clarity, just we are going to show look like finite angle, but definitely it is not so. So this vector is rotated, say comes here. So this angle is say d theta. Look at d theta, how look like a 30 degree. So that's the way we are going to understand the change of this vector. So this is the r vector, say taken as r1 vector, and this is taken as r2 vector. However, mod r1 vector is equal to mod of r2 vector. Look at here. So just we are going to find the change. R2 vector minus R1 vector. How one can find this change? Like that. This is taken as say delta R vector. The change of this. Delta R vector comes out to be R2 vector plus of minus R1 vector. Look at here. So this one, the scalar multiplication of vector comes out to be the minus sign. So there is no change in the magnitude. This is also equal to mod of minus of R1 vector. But direction has been changed by 180 degree, means opposite to the vector R1. So this is minus R1. This is d theta, so it comes out to be 180 degree minus d theta. R2 vector plus of minus R1 vector. Firstly, we want to find modulus of that. What will be the modulus of that? Modulus of R2 vector whole square, modulus of minus R1 vector whole square, twice modulus of R2 vector, modulus of minus R1 vector, and cosine of the angle between them. What the angle between them? Look at the figure. This is the angle between them because this is the vectors diverging from this point. So this is the angle between vectors. Cos 180 degree minus d theta minus d theta. So look at here. This is, say this is the radius circle taken as a small r. So this is r square twice r square 180 degree or 360 degree function. Cos give you cos d theta. Okay, but this is in the second quadrant, so put the minus sign here. This is root 2r square root of 1 minus cos d theta. So this comes out to be root 2 into r square root of, this is twice sin square d theta by 2. Now it comes out to be modulus of delta r vector is equal to root 2r, then again root 2, and the mod of sine d theta by 2, which is positive, so no need to put mod. Take it out, comes out to be sine d theta over 2. As we know, if theta is very small, here then infinitesimally small and divided by 2, so it is very small, so it may be written as d theta over 2. So it comes out to be r into d theta, r into d theta. Okay. Say, what about the direction? What about the direction of delta r vector? Delta r vector. Look at d theta is very small. We are able to see by any magnifying microscope. It means here. Okay, so it becomes almost perpendicular to vector r1. Almost, or you may call it tangential. You may call it tangential because the chord, and this is the chord length and this is the arc length. How these two are equal? No way, because d theta is infinitesimally small. So you might say this is the delta r vector tangential to vector r. However, it is strictly speaking not so. But in physics, we apply what is called in loose sense, not a strict sense. So here is the delta r vector. Okay, so in this direction, you may call it here is the dr vector. Why not dr vector? Like that, tangential to that. So we are going to use the formula. So here the vector r, and there is a vector of angular momentum L. So just we are going to find the change of that. Look at in which way. So these are the things how one can find the changes of the rotatory vector. Okay, just we are going to apply this result there. So what is the result here? R d theta. What does it mean? L, in case of the rotation of the angular momentum vector, L d theta. Look at how and why. So in this way, just we are going to indulge this result. Before indulging in the main problem, just one more input is here, is that however this notation is little bit higher than what we are discussing in class 11 and 12, but I have to show torque is equal to I alpha not always true. So for the sake of that, we have to take this very interesting but very small article. Look at here. Suppose we have a body. Suppose we have a body like that. Say this is the body. This is the body. Might have been under translation, might have been under rotation, like that. Maybe anything. Look at again here. So this is, say this is under rolling. Look that under rolling, rolling like that. It means it is translating as well as rotating. So we have to deal the motion of this round body by taking any point in this space. Might have been any fixed point in this space. We may take point, or we may study by taking the point inside the body. If we take the point inside the body, then why not center of mass? So we have to take the center of mass. Okay, so we have to take the two way to the center of mass. One way is that we have to take, say here is the center of mass, we take particle here, so we have to make the radius vector there in this way, if you rotating like that, anyway like that, or anyway. Okay, and this center of mass, the body, we have to measure the angular momentum or any related quantity to that with respect to the body or with respect to the point in a body which is very interesting center of mass, or we may take any fixed point in space. Okay, and also the particular point or whole points motion with respect to center of mass. So the relation is this. Look at here. So we may apply in any vector. So here d by dt of some vector fixed point in space, which is equal to d by dt of by time, because this quantity or this vector which are going to appear, or maybe a scalar, is time dependent. D by dt of something here with respect to the body and plus angular velocity, because it is under rotation. If not, then remove it, translation then okay, no problem, and of that vector measured with respect to the body. This is the relation. However, it came through very easy way. So transformation equations, okay, Galilean transformation equations you may find. We will see in very detail when we take up rotational motion, but right now we are taking the help of this relation. Okay. So what we are going to study here? So d by dt of angular momentum about some space point, fixed space point. This is equal to d by dt of the angular momentum with respect to the body. You may write here space like that, and plus omega cross L body, because body, also body. Look at it. These things here, this is known as tau. This is the actual definition of the torque, not torque is equal to I alpha. This is the equation by which we govern the torque. Torque is not related all the time by torque is equal to I alpha. Torque is equal to I alpha. But in general, we all know torque equal to I alpha. All the time it is not related to that. That is why I am telling you. Now look at here. Now, so here the space point, here is the body. So just we want to write it down here. Torque is equal to d by dt of LA. Look at here. LA. We want to resolve this angular momentum vector horizontally and vertically. Which way? Look at here. Again you have to see here. So what is here? Here this is the length, this is the angular momentum vector. Say this is the vertical, this is the vertical, and this is the horizontal. Look at here. This is the horizontal and this is the vertical. Look at here. Vertical and this is the horizontal. This is the L vector. All the times like that. All the times. Look at here. Look at here. Look at here. Look at here. All the time like that. But this is the constant vector in magnitude, but changes direction. So a vector will change, either change in magnitude or direction or both. So here the magnitude is fixed, which is not changing. Length of the vector is fixed, but direction changes all the time. So this vector changes. So we have to take the component of that, horizontal and vertical, like that. So d by dt of LA horizontal vector plus LA vertical vector. So we write d by dt of LA vertical vector plus d by dt of LA horizontal vector. Now here what we have been derived, the torque is equal to d by dt of vertical vector component of angular momentum plus time derivative of horizontal component of angular momentum vector. So now look at here, this is the magnitude of delta r. So just we want to write firstly in terms of its what is called vector. So look at here, delta r vector this comes out to be delta r magnitude times unit vector. So unit vector is perpendicular to vector r1, means in the direction of tangent. So here this is the unit vector in the direction of tangent. So here r multiplied by any infinitesimal quantity. So we may write here dr vector as what is called r d theta into tangential unit vector n. So we have to use this result here. Let us see firstly, this is d by dt of the vertical component. It means, look at here, this is the angular, look at here, this is the angular momentum, this is the length of the string, say taken as r vector. So this is the vertical, look at here, and this is the horizontal. Okay, so its component vertical direction, so here LAV, here is the horizontal component. So in this direction angular momentum, its time derivative is here, and we have been seen angular velocity vector is upward. So this component, vertical component of the angular momentum vector and the angular velocity vector in the same direction. So we may replace this one as per rotational dynamics as I omega, I moment of inertia, also about this axis, vertical axis. Here is the bob, so we have to find the moment of inertia of this bob with respect to that vertical axis. So that is LAV vector is equal to I omega vector. So we write here like d by dt of I omega vector. So what this is d LH over dt. Now just we are going to use this result. Look at here, this is the torque is equal to, so here the moment of inertia taken as a constant quantity, take it out from the integrand, so is that I d omega over dt plus dlh by dt. So dlh is like that of dr vector, so write here L, that's the magnitude, into say there d theta over moment. So look at here again, so look at here, this index finger is the horizontal component and this rotates, so rotates this way, look at here, rotates in that way, look at here. So this horizontal component vector, which is angular momentum vector, the component of this angular momentum which is perpendicular to that, the length of the string, the radius vector. So this horizontal component is rotated. So that is why we are going to write here L like that of r d theta over dt. And what about unit vector? Unit vector like that of tangential. In horizontal circle, tangential like that. Okay. So say this is the unit vector n. So as we know here, angular velocity is constant. Why constant? Because at certain angular velocity, just I maintained, you may maintain once you are performing the experiment. Okay. So here it comes out to be, here firstly we are going to write I alpha at L, this is at omega into unit vector n. So this is L. What about L? Not the total angular momentum vector. This is the L horizontal. L horizontal. In fact, here L AV. So just put it here A. So here not L, the L AH is also L AH. So angular velocity is constant. So its time derivative is alpha. It comes out to be 0. So here this is I into 0, and now this is say ditto. Now this is 0 plus this vector. So it's the identity vector here. So this is the LH omega n. So now what I've told you earlier, all the times torque is equal to I alpha and we consider it as this is the equation, and we have to apply, or we always try to use when angular acceleration, moment of inertia and torque etc. are given. So it is not the case, because we not ignore this one. Not ignore this one. So what does it mean? Torque not all the time I alpha, but in terms this the second term must be taken into account. So if this second term we may not take into account, once we consider here is the angular momentum vector, in that direction is say omega angular velocity, so torque equal to I alpha is valid. If angular velocity changes, then it gives you alpha. If not, then torque comes out to be 0 as per angular acceleration is 0. But in this particular case, look at here, that one of the component of the angular momentum, that is the vertical component, is not changing, but the horizontal component is changing as time passes. So that is why this is the equations we are frequently using, and this one is the that differ what we are applying frequently. So this result, torque is equal to time derivative of angular momentum with respect to space fixed point. Keep in mind, space fixed point, not the body fixed point. I have written the result earlier. So this result in this way, or in the specification, space point, body point, so these are we may take into account when we deal undergraduate physics. But here in case of class 11 and 12, just we settle myself, torque is equal to I alpha. But here one of the problem, conical pendulum, so we have to consider these two terms as well, and maybe in many more cases. So what we are studying in class 11, 12, it is all over. Still more to know in graduation as well in the MSc physics. Why not after that? We all try to become a scientist. Why not? So, what we are knowing is nothing, because to know, universe is left. Now, we are going to the last one, is that, look at here. In terms of a problem, just we are going to take the conical pendulum in case of a massive rod, massive rod. So, this is the mass m distributed uniformly. This is a rod of mass m distributed uniformly, length is L, and this rod is in the form of a conical pendulum rotating like that. See, like that of conical pendulum. Once its angular velocity is omega and keeping constant, then we have to find this rod makes an angle alpha with the vertical. Look at here, this is the vertical and this is the rod. Then we have to find this angle. When angular velocity of this rod, or in fact this conical pendulum, when become constant, then this angle will not change, and now we have to find this angle. Okay, this is the problem. How one can find this one? Look at here, how we are able to find this one. Look at here. So this is the rod. This is the point of suspension. So this is the angle alpha we have to find. This is the angle alpha we have to find. The rod has mass m, length L, rotating with the angular velocity, constant angular velocity omega. We have to find this angle alpha. How is it possible? We work it from the ground frame. Then, is it possible? What we have to do with the ground frame? We have to find the omega, time period, balancing the vertical forces. You may try also from ground frame. Then you will not find any independent relation by which this angle alpha comes out to be. So, as myself tried hardly to find this angle from the ground frame, but still I am not successful for that. Again we will try. If it comes out to be, then I will show you in the next class. But right now we are going to find this alpha in the frame of rod. That is, the frame, we have to take a frame which is as good as this rod, rotating rod. What does it mean? It means rod is static in my frame, or we sat on the rod, supposing my weight, your weight is negligibly small, and then find this angle alpha. Okay, just we are going to find out. So because we need a relation which is balancing each other. So firstly, let us see, because the frame is rotatory, any rotating frame is non-inertial in character. Any rotating frame non-inertial in character. So if frame is non-inertial, then we have to think of pseudo forces or centrifugal forces. Centrifugal forces. Okay. So firstly, we want to find the torque due to the mass, weight, rod mass means the force of gravity acting on this rod of the mass m. So this the rod is uniform, so we have to take the center of mass. That's okay. Here is the center of mass. Here is the mg. Okay. And now this is the point of suspension. Say we have to find the torque of this mg about the point of suspension A. So here is the line of action of force. Look at here. So this is the moment arm. So take the moment arm as a vector. So rotate vector r towards mg. So it is going inta. Going inta. It. So here, what is this? This is the moment arm, and it comes out to be L by 2 sin alpha. L by 2 sin alpha. So torque of mg force is comes out to be what? Mg is multiplied L by 2 sin alpha, but going say into the board. So here circle cross like that. It is a vector. We must have to write the direction as well. Otherwise it is wrong. Definitely wrong. Because in one of the examiner asks you find the velocity and you are writing only 5 meters per second. What does that mean? You are wrong. 5 meters per second in which direction? In which direction? East, west, north, south, up, down, at some angle. In which direction? Then you have to write direction as well. So that is right. This is the direction. Now we have to find the torque due to the centrifugal force. How? Let us see here. Say for this we have to take at a distance x here, cut the length dx. So this is here, say a small r. In this direction there is a centrifugal force. Centrifugal force. This is say taking the length x up to x here. What is the mass of this length dx? It's called dm. Mass per unit length, m over l into dx. Here centrifuge, say a small df. This comes out to be magnitude. We are writing here m omega square r, dm omega square. This is small r here. Majority of the people are thinking omega of this dm mass. However, in this case too, is the dm is the angular speed of the frame, not of the mass. Keep in mind. However, in this case, rod is itself rotating, altogether different issue. So dm omega square r. So this is the force, and now this is the line of action of force, and here is the moment arm. What is the moment arm here? X cos alpha is the moment arm. What is the direction? Look at here. Up. Okay, up. the torque of centrifugal force is what? However, this torque is, because we are taking the df force, the d tau, infinitesimally small torque, comes out to be df, mod df there, dm omega square small r. What is small r? Look at here, x sin alpha. And the moment arm is x cos alpha. Then it comes out to be here, dm is what? M over L into dx, here omega square x square sin alpha cos alpha. So integrate it, but as I have taught you earlier, once you are dealing vector, you must care about the direction. So I have missed the direction. Take it into account. So here a dot in a small circle, 0 to L, and it comes out to be, keep out constant from the integrand, omega square sin alpha cos alpha, sin alpha cos alpha, m over L, here x square dx comes out to be x3 by 3 plus antiderivation constant, upper limit minus lower limit, and it comes out to be a small L cube over 3, L cube over 3. So cancel one of the L because it is defined and not 0 as well. This is omega square sin alpha cos alpha m L square over 3. So torque due to the gravitational force acting on the rod is vertically down. You may say here inter the board, and the torque due to the centrifuge, because we are working from the rod's frame in fact, which is accelerated, rotating frame, accelerating frame. In fact, horizontal acceleration, there is a change in angular momentum, there is a torque, not vertical, horizontal. That is why it is accelerating. Okay. So this is the case. These are the cases, centrifuge. But once we sat on the rod, or we are working from this rotatory frame, so rod's angular velocity, because as the rod rotates, as we rotate together with them, together with it, so there is no any vertical acceleration, angular acceleration. There is no any vertical angular acceleration. What is vertically? Because this is the on the line. Say rod is rotating on this, like that, rod is rotated like that. So we are talking about that, vertically up, vertically down. So net torque must be 0 because there is no vertical angular acceleration. So what we have to write here? There is no any angular acceleration in the rod's frame. There is horizontal torque from ground frame. When we are in the rod's frame, there is no any angular acceleration. What does it mean? There is no any angular acceleration in the rod's frame, and therefore net torque must be equal to 0. So equate it. Omega square sin alpha cos alpha ml square over 3 is equal to what? Look at there, mg L by 2 sin alpha. That's okay. So m is cancelled out from here. Yes, 1L, okay, cancel from here. One of the sin alpha as well, because alpha is some angle there, acute angle as well, not zeroed but defined. So cancel like that. Look at the sign of cancellation. Okay, so this way, that way, and cross way. So if one saying this calculation, then okay, if we cancelling on the same signs, then sin alpha may be cancelled by L. One may arise a question. That is why this is the art of calculation. Keep in mind. So now here cos alpha is comes out to be 3g over twice omega square L. So this is cos alpha and hence alpha. So we have to find angle alpha. So alpha is equal to cos inverse, is the way of write in terms of inverse, 3g over twice omega square. So this is the conical pendulum. In fact, another version of the conical pendulum. Okay. However, still some types of pendulum is still left. So that's I am going to keep it stop here. Discussion of the time period of pendulum. So in this series we have taken simple pendulum, physical pendulum, and as well as the conical pendulum. Okay, in case of a simple pendulum, linear and non-linear one as well. Okay, so that's I'm going to finish this lecture here. The time period of conical pendulum. We will take the next class for the discussion of the Coulomb's law. We have to go through the vector. So hopefully we will take the next class of vector. Okay, thank you.